Now, I would like to invite my colleague, Dr. Mohammad Moss, to moderate the first session of this FDP and to introduce our esteemed speaker, Professor A.R. Mohanty.
Thank you, Mr. Atib Ahmed Khan Sahab. This session is based on past. For this session, our renowned speaker will be Professor A.R. Mohanty, professor from IIT Kharagpur. Professor Mohanty has more than 30 years research experience in the areas of machinery, condition monitoring, and acoustic. Professor Mohanty's research group does both fundamental and applied research. The research activities carried out by the group is done with an objective of providing immediate solutions to an engineering problem in hand. Some of the current research activities in the areas of acoustics are in the development of new natural acoustical materials, acoustical metamaterials, acoustical holography, microperforates for noise control, acoustical source localization, underwater acoustics, and signal processing. The research in the areas of machinery fault diagnosis are in the areas of fault prognosis, incipient fault detection, instantaneous angular speed estimation, empirical mode decomposition, model-based fault detection, remote sensing, wireless data acquisition, and motor current signature analysis. Now I would like to welcome Professor A.R. Mohanty to please deliver his lecture. It is due to Professor Mohanty, sir.
A very good morning to all. At the outset, let me thank the organizers for having invited me to deliver a couple of talks on your FDP on this machinery condition monitoring. By the way, certain queries, am I audible? Am I clear?
Yes, sir, you are clearly audible.
Okay. If you will allow me to share my slides, can I do that? Yeah. Yeah, well, the slide comes up. I was sitting through the introduction, inaugural ceremony. Could the organizers give me a feel of the background of the participants? You know, that would help me deliver my talk at what level and so on. I will appreciate if the organizers can give that. The problem in this online mode is, you know, it's always a one-way communication. So being teachers, we love it both ways, but I can understand because of this COVID situation, we have to do it this way. Nevertheless, if I can get an idea on the background of the participants, that would help me.
So the participants are faculties from different colleges, ranging from north to south and all across the country. Assistant professors, associate professors, as well as we participants from the industry. And few of them are students, wherein we have research scholars and PG students. There are few in number, but mostly are faculties from design, automation, machinery condition monitoring, mostly related to the area. So,
okay. Yeah, I'm still waiting for my slides to open up. See, I have a presentation in the morning and also in the afternoon. So I will make it flexible and I will welcome the participants to ask me questions whenever they feel like. And till the slide comes up, I will maybe brief you about what this is all about and where we are in the present world. So as you all know, machinery condition monitoring, the very best analogy is you become machine doctors. Okay, we are actually doctors for the machine. Think the machine as a human being. Okay, so when a human being falls sick, he or she goes to the doctor. And of course, doctor measures the body health parameters, finds out what kind of sickness one is having, and then prescribes corrective measures by giving you proper medicine. And then, because in many cases, the fault prognosis part is, the doctor will say how long is your sickness going to be, or how long will be your term is going to come to an end, or something of that sort. Okay, coming back, is my slide visible?
No, sir. No, sir, it's not visible.
It's not visible.
No, sir, it's not visible.
Okay, I shared my screen. Last slides. Is it visible now?
Yes,
Yes,
sir.
sir. Yes, sir, it's
Okay.
visible.
Yeah, thank you. Okay, now see, I'll be talking on this topic of past, present, and future of condition monitoring. And by the way, if you need to contact me, the participants, I'm available over email and over mobile as well. And you can go to my website, iitnoise.com. Now, before I begin my talk on the past, present, and future of condition monitoring, I would like to give you an outline of what I'm going to present in this sessions on condition monitoring. And wherever you see all these topics, I will be discussing about the history, the origin of these techniques, what is the present status, and what perhaps would be the future. I did hear your Dean Sahab mentioning about IoT and Internet of Things, Industry 4. Yes, that is true, but let us look into Industry 4 as to how it is going to help machinery condition monitoring and what are the nitty-gritties in Industry 4 and how actually it is helping us remotely monitoring machines. Today, let me tell you, sitting in a lab or using your phone, you can, sitting in India or in Aligarh or in Kharagpur, on your mobile, you can get the parameters of a gas turbine working in Alaska, okay, or a wind turbine working in the North Seas. You can monitor the gearboxes of those wind turbines or the generator coupled to the gas turbine unit in Alaska. So this is all very much possible. I mean, having said that, again, you can understand earlier, I'll come to that, earlier the analysis was done on computers, and you all can relate that computers have become so small, the computing power in your iPhones today is much more than the mainframe computers which came up in the late 60s. Okay, that is the power. And this has all been possible by miniaturization, availability of high density VLSI chips. So electronics industry, aided with the computational facilities, the techniques of computation, fast computing, has taken us to a level where, which would have sounded like a science fiction about 3 decades or 4 decades ago, is where we are. And at the end, if you think what the future will be, you will be surprised. And already people are working in that area. So now, just to give you a dimension, I'm sure of those of you who have practiced condition monitoring must have seen, cables running out of machines, going to an analyzer. Today, it will be all wireless. In the future, it will be all wireless, no cables. Wireless, and there are some speed restrictions. We will come to that details when I talk about. And that is the future of condition monitoring. And why only that? Today, the technology is such, if you have a refrigerator in your house or on any home appliance, your air conditioner, you don't have to worry about their health. The service technician will come knocking at your door, telling you, well, your refrigerator compressor has a problem, or your split AC is going to leak water in the next 2 days. Okay, and that's the problem which you all have. And this is all possible. This is all possible, and the technology exists. And today, you won't believe it, the home appliance manufacturers have really taken IoT and condition monitoring to the next level. We are working with many of these home appliance manufacturers. They are looking for smart, small sensors, low cost, but these sensors will measure the right parameters, and then they will transmit the parameters over Wi-Fi, computation in the cloud, a lot of data analytics, machine learning, and then they will come up with a prognosis that this blower, there is going to be a problem with the motor, so please fix it. And this is what the technology is going to be. You don't have to call up a service technician once the machines are down or once your home appliances are down. So machinery condition monitoring is just not large steel plants and cement plants and power plants. It is in our daily life. So you can understand the scope of this field, and those of you who are students or young researchers, the future is tremendous, very big. It's a many billion-dollar business, IoT business, close to about 500 billion US dollars. So the future is great, perhaps, but at the same time, when I say future is great, the laws of physics should never be violated. I mean, the basics of machinery vibration is going to stay. But only thing is that which has helped us or which is helping us is the availability of tools, processing power, and sensors. And that is going to help us along with availability of the machine learning techniques, wherein a lot of data can be handled and features extracted, analysis done to prognose remaining useful life. Fault prognosis is very important. I mean, today the physics is such that everybody understands more or less by measuring the vibration or measuring the motor current or measuring the temperature, what is the problem. But if you go to the industry, if you go to the plant management is going to ask, how many days am I going to survive with this equipment? They will ask you, sir, or kitne din hai before I change this equipment? And that is very important because it eats into their capital budget. So fault prognosis is an area where researchers throughout the world are working. This fault prognosis is through physics-based solutions or through simple analysis like regression, or even using soft computing techniques of machine learning. And they can very easily predict the end cause. Again, to give you an idea, I mean, I'm just widely telling you all so that just to excite you, to tell you, to let you think your own way. I mean, imagine the supply chain logistics problem which we had because of this shutdown. And today, of course, again, we are perhaps we do not know what is going to happen in the next couple of weeks. But nevertheless, there is a worldwide shortage of semiconductors. And because of the manufacturing plants, which are mostly in China and Taiwan, where went to a lull and there is a demand for it. But if you go to the ports, the cargo ships which come, we cannot be holding them on the berth for loading and unloading for a long time. So they have to be very efficient. You just realized that last year we had a problem with this ship getting stuck in the Suez Canal because of whatever be the reasons. I'm not going to the reasons, but would these things have been avoided by proper monitoring of the navigation system or having proper warning systems on board the ship? So you can see condition monitoring in some way or the other is affecting us in our daily life, affecting us globally, and there is a definite process, technique, and the intent of my talk here is to give you an overview of where we were, where we are, and where we will be. And with reference to, in the afternoon, we have mostly on the recent advances in instrumentation. So I'm going to mix some of these techniques now and some later on. So anyway, this coming back to my presentation, formal presentation, I'll be talking about, again, condition monitoring. If you look at it, there are many ways we can do condition monitoring, be it vibration monitoring, or if you look at the oil in a gearbox, or the lubricating oil, or the hydraulic oil in the hydraulic systems, it is the wear debris collected in the oil and the oil analysis itself. So loosely it is known as wear debris analysis. So globally, 70% of the machinery condition monitoring is actually being done by vibration monitoring and 20% by wear debris analysis. But in the last 2 decades, this technique of motor current signature analysis has come up, and we at IIT Kharagpur were the pioneers. Somewhere around 1998, I discovered that this is possible. But then when I looked into the literature, and there is nothing novel in it, the physics says that yes, it is possible, but somehow people had not taken it to a level where it is in this present scenario. But again, having said that, it is not that I discovered or I invented motor current signature analysis. We looked into the literature somewhere in 1974 in the Oak Ridge National Laboratory in US, in the nuclear reactors, when they were opening servo controlled valves, there is a reference that they measured the motor current of the servo motor current, and they could realize if the valve closed or opened looking at the motor current of the servo motor. So when we tried to, obviously we could not patent it because it was not our idea, but then we took it further. I will come to that story later on. So this, what I meant to say is, this motor current signature analysis is a technique which is coming up. And another technique which is very strongly coming up is again thermography. You remember, earlier we used to measure the temperature of blast furnaces with pyrometers, radiation pyrometers. Looking at the filament color, we could match in the background and measure the temperature. But again, with the development of electronics and availability of semiconductor materials, which are which give out certain voltage when an infrared beam is incident on the semiconductor. So today, you have a lot of handheld cameras, infrared cameras, wherein you put a semiconductor array of some pixel arrangement. So depending on the intensity, heat intensity, coming from the Stephen Boltzmann law, at that area, you can know the absolute temperature to the power 4 of the body from which this infrared rays are being emitted, and then we can find out the heat source or the temperature at any remote locations. Again, this is very, very popular for a quick survey, particularly electrical loose contacts, because if there is a loose contact, if there is a sparking, there's a lot of heat generation. Imagine all the power line transmission in your switch gears, the power transmission system. If there is energy loss because of heating and because of loose contact, that all could be saved. And because of excessive heating, the conductors may melt with time. So I will be talking about some of these techniques and then what is the status. And then of course I will end with the future of CBM. So the existing techniques, some companies will be only doing maybe vibration monitoring of the machines. They will have an equipment, they will have a transducer, measure the vibration, find out the physics-based reasons why, what kind of problems is there. If a machine is rotating, it is supported on shafts, it is having shafts which are supported on bearings. So if the shaft has an unbalance, shaft has a misalignment, shaft has crack, the vibration response at the bearings is going to change. So we will measure it with a vibration transducer. Now coming back to the, I'll come back to that vibration transducer just in a little bit. And then I just mentioned about wear debris and all analysis. And we talked about a brief introduction of what is this motor current signature analysis, thermography, and a lot of NDT techniques are also people are using like ultrasonics, X-rays, acoustic emission, etc. to finding out the present fault condition. Now, as I was telling you, if I have the present fault conditions, I have the past conditions, through proper mathematical tools, I can predict the future. I can know that predicting the future means the remaining useful life as to how long my machine is going to survive before it is sent for a repair. So this is in general the arrangement of CBM. I have a machine, I have a regenerative machine. I put a transducer. Okay. I put this transducer, and then I see some questions are coming up. So what I will do, I will keep the last half an hour for this question and answer session. Is that okay, Dr. Sidra? Yeah, I think I will keep the last half an hour for question and answer. And then of course the transducer measures this signal. Certain conditioning could be there. Is it necessary, for example, amplification, linearization, removing certain noise. And then once we have the nice clean signal out of this machine, we do a lot of signal analysis, be it in the time domain, be it in the frequency domain, be it in the time frequency domain, and so on and so forth, and try to find out the fault in the machine. Now, I will come to vibration monitoring, the origin of vibration monitoring. See, in the early 19th century, people were using steam turbines, okay, for power generation, and that was the only machinery available for power generation. So there was one scientist, Rathbone. He wanted to know, like, how do I know the condition of this turbine? And he was with General Electric in US. And somewhere in 1920s, what he did is he put a simple electromagnet, okay, on the casing of the uh, turbine, and which we now know as the velocity pickup. Okay, that is a simple velocity pickup. If there is a motion here, this coil is going to, this device core is going to move, and there's a coil. So there will be a voltage proportional to the movement here. And that was a very rudimentary way of measuring vibrations. Nevertheless, there was no other equipment available, no accelerometers were that popular, though in 1920. The theory of accelerometers did exist, but in the accelerometers required a sensing element. Of course, today we have piezoelectric crystals as the sensing element. In those days, in 1920, they were actually strain gauge based device. Okay. Strain gauges were put as sensing elements in accelerometers. Okay. And so what happened? This gentleman, Rathbone, he made some charts, okay, as to, for example, he made some charts as to what is the vibration level, okay, as to what frequencies and the power, whether it is rough, it is smooth, whether it is acceptable, etc. This was somewhere in the 1940s, the vibration severity chart. And these were all made from velocity measurements on the casing. Okay. But this was quite not right, because once, as you all know, the dynamics, the rotors, when they are rotating, they are placed on the bearings. So actually the bearing vibration gives us a better picture as to what is the condition of the vibration. So they made an attempt using the strain gauge based accelerometers. But at that time, in 1940s, Chrysler Instruments in USA, Switzerland, they discovered that this piezoelectric equipment, piezoelectric material, is a better sensing element for accelerometer. Okay, so they measured the acceleration. I'll come to that in a little bit. But at the same time, again in 1940s, Mr. Bentley of Bentley, Nevada, found out by putting such non-contacting eddy current probe, and if there is a play or radial play in the shaft of a turbine, and if I plot the x versus y between these two transducers which are 90 degrees to each other, I will get different shapes depending on the radial displacement, and which are actually known as orbits. So they started to do orbit analysis. Okay, they were in parallel, the Bentley Nevada orbit analysis for finding out faults in turbines. Even to date, they are non-contact, and that is why they are even popular in the present turbines, the present steam turbines. But parallelly, with the development of this piezoelectric accelerometers by Kessler in 1940s, somewhere around late 40s, one gentleman, Bruel and Kay of Denmark, two gentlemen in fact, Bruel and Kay of Denmark, they first produced the commercial piezoelectric accelerometers in 1949, I believe. Okay. So accelerometers were made available, and then people could measure the voltage output of the accelerometer. They were actually charged type of accelerometers, so they required a charge to voltage accelerometer. They require a charge to voltage amplifier. And in the accelerometer, if you look at the cut view, this is actually a piezoelectric crystal. Okay. So this was what was the in 1940s, and of course, even till today, we use piezoelectric accelerometers for measuring vibration. This is in one direction. There are accelerometers which could be measuring acceleration in three directions. They are known as the triaxial accelerometers. The casings are hermetically sealed and so they can be used for, they do not get contaminated. They can be used in very, very high temperature. Today we have accelerometers based on these piezoelectric crystals, which can measure up to 500 degrees Celsius. We have, and they're very expensive, by the way. For example, if you want to measure the vibration of a helicopter engine on flight, so these kind of accelerometers are available. And of course, they come in different sizes, shapes, sensitivity, etc. But parallelly, I was talking about this orbit analysis, which is also very popular. You can, this is a rotor with an unbalanced mass in our laboratory. Okay. You will see a normal condition rotor. Okay. There is some resident imbalance, unbalance. So you see this small magnitude, 1.94 micrometers per second square is the level of acceleration. But with the unbalance, you see 33.4 micrometers per second square. The orbit increases. So this is very popular even in the shop floors today. If you go to any turbine manufacturer, be it BHEL, etc., in their test plants or test rooms, you will see they put eddy current proximity probes at different stages of the turbine, and then they monitor the orbit. This is very easy for the technician to just look at the plot and see if the plot has gone big, the orbit has gone bigger in diameter, or the ellipse has expanded. You know that this is a problem with the shaft. So what I'm going to say is that today the technology is such, we have piezoelectric accelerometers, and then we have the orbit analysis. Okay. But another technique, I'll come to that later. The accelerometer being a contact type equipment or a sensor. Eddy current is not a contact type, but the frequency range of the accelerometers is very, very high. I can measure very high acceleration levels, and also the frequency range. So today we can use accelerometers for measuring vibration, and all of you know that if I have a vibration measurement system, I can measure the acceleration in the spectrum. Suppose the acceleration is amplitude is a omega square, where a is the displacement amplitude, a omega square becomes the accelerometer amplitude. So a omega square divided by omega is a omega, that is velocity amplitude. A omega divided by omega is a, that is the displacement amplitude. So whenever I measure acceleration, very easily I can obtain the velocity spectrum and the displacement spectrum if required. So today the industry standard is everybody measures vibration using contact type vibration transducers. Having said that, the problem is these piezoelectric accelerometers are very, very expensive, but many a times we require to measure acceleration at very, very low frequency levels. For example, deployment of an airbag in your vehicle because you are fast decelerating because of an impending crash. Because deceleration rates can be measured, but they are all very low frequency phenomena, less than 3000 hertz. So today the technology is such that these MEMS-based accelerometers are becoming very, very popular. But I must caution you all, machinery condition monitoring engineers who are using accelerometers for monitoring health of turbines, gas turbines, very high-speed moving equipment. We have to keep the temperature, the frequency in concern, and also they cannot be subjected to very, very high temperatures, right? So that is why these MEMS-based accelerometers you will see in your mobile phones. They are actually MEMS-based accelerometers, okay? And shock detection accelerometers for deploying in something. These are very, very popular. Okay, limit type accelerations. But for actual condition monitoring, one restriction is the frequency, other is the temperature. But having said about accelerometers, again, you all know the Doppler effect. Okay. So scientists have discovered or have identified what is known as this piezoelectric accelerometers. The laser-based vibration vibrometer, wherein I will use a laser-based vibrometer. This is a refrigerator compressor. I'm shooting a laser beam. So this is a laser beam of a particular frequency. And if this body is having a vibration, so imagine this is your target. So this laser beam will get reflected back with a Doppler shift, which is a function of the velocity of the surface. So if I have the correct optics in my optical element here, I can measure if the frequencies of the laser beam are known to me, if I can measure the Doppler shift in the frequency delta f, I can find out the velocity of my target. And that is the principle behind single point laser vibrometer. Of course, the problem is they are very, very expensive. Just to give you an idea regarding the cost, if I talk about a MEMS-based accelerometer, they'll be less than about less than 5,000 rupees. If I talk about an piezoelectric uniaxial accelerometer, somewhere around 30 to 50,000 rupees. But if you look at a single point laser vibrometer, this device along with this analysis unit costs somewhere around 10 lakhs of rupees. So they are very expensive at the moment. We do not know what's going to happen in the future. But such single point laser vibrometers do exist. And of course, all these measurements which we have talked about, they were all for linear measurements. So again, people have started to find out that in condition monitoring, because see, actually the faults which are occurring in the shaft is because of torsional vibration, the speed fluctuation, because of a fault, because of a crack, because of a bearing fault. So this could be best measured if I can measure the torsional vibration. So this was the idea behind, if I have two laser beams, I have two laser beams, okay, separated at a distance d. Okay, this d is known to me. This is the wavelength of the laser beam. Okay, and I can know the frequency omega of which this is rotating, and these are very instantaneous. And this Doppler shift between these two beams can be measured through the optics of a rotational laser vibrometer. So this rotational laser vibrometer, this is actually the head, okay, where two laser beams come out like this. Two laser beams come out, and this is my rotating shaft. I can measure the 1/20,000th of an RPM of this shaft. Okay, so and it can measure fluctuation in the rotational speed. When I say rotational speed, actually it is torsional vibration. So this torsional vibration can be very easily measured by rotational and laser vibrometer. And this is again, these are very expensive units, about 30 lakhs. So you can imagine the cost is prohibiting us to deploy them in the field, but nevertheless in the R&D, etc., people are using, particularly wherever you have, when you have a rotational laser vibrometer, we can, I will come to the questions later on. I can see questions popping up. I will come to the questions at the end. But then keep giving your questions on the channel. So when I come to the rotational laser vibrometer, suppose I have a plant. I'm producing transmission axles. when the plant is manufacturing transmission shafts, whether they are within their vibration is within limits or not, in an end of the line testing, you can have the transmission shaft powered, and you can always measure the torsional vibration. If it is within limits, it is accepted to be put in your truck. So this kind of one of a kind setup, people are putting it in many plants. I've seen brake manufacturers, axle manufacturers, and differential manufacturers. They are using it for testing. Of course, in the lab, we use it for measuring the torsional vibration. Of course. Yeah, I just saw a question quickly popping out. If you want to, can you measure translational vibration? Oh yes, you just switch off one, and those options are also available in the rotational laser vibrometer. Now, another technique which is very popular, again, these are all recent developments in the from the laboratory. I mean, we started with the casing vibration in the 1920s and 40s of a steam turbine, and today you see we have MEMS-based accelerometers, we have rotational laser vibrometers, we have linear transverse laser vibrometers, and we also have optical encoders. Okay, so as you all know, optical encoders means if you have a disc with slots on the periphery, and this is rotating. If I put a light at one end and a photodiode at another end, if this shaft was rotating at constant speed, I would be getting a pulse which are equally spaced. But if there is a momentary change in the speed, this width is going to change. Okay, and by taking a derivative of this, I can find out the instantaneous angular speed. So today we have encoders in all the lathe machines, all the manufacturing machines. So just by processing this pulse, I can measure the instantaneous angular speed. And we have been using this in faulty gearboxes. And through the instantaneous angular speed, I'm able to detect faults in the gearbox. If I put it in an engine, I'm able to detect the engine firing frequencies. So these are all possible. So this is the how the instantaneous angular speed can be given, and of course the RPM can be calculated. This depends on the pulse generation, etc. I will not go into the maths of this. In the handouts which I have circulated to the organizers, I have given list of some of the bibliography, some of the papers of ours, where the details, techniques of these are given. So those of you who are interested can access those journal publications and see the actual theory behind the instantaneous angular speed measurements using optical encoders. Of course, you have to keep in mind is the sensor resolution. By sensor resolution, I mean how many pulses per rotation? Is it 1,000 pulses per rotation, etc.? Okay. What is the sampling frequency? The only issue is here is we have to measure at a very, very high sampling to get a best estimate of the rotational speed. But by the way, so far we have just discussing about the sensors. Particularly, I discussed about the acceleration measurements, and of course the rotational torsional vibrations, and how using RLV and the optical encoders. But I just briefly go through this experiment which we did in the laboratory. If we are meeting, I mean, I could have, when it's in Kharagpur, students get to see the lab and the equipment. Of course, what I have planned is towards the end of today's presentation, I will give you an overview of the facilities at our lab in IIT Kharagpur, in particular the acoustics and condition monitoring laboratory. What are the facilities which we have, and what are the experiments which could be done, and so on and so forth. So in this, we have an induction motor, which is driving a DC motor, and there is a variable resistor load bank loading the generator, which is driving a gearbox. And if you see here, at the end of the generator, this is the gearbox motor cover, and at the end of the generator, I have put the encoder, and then we have the data acquisition unit, which will correct the pulses. It's a better view of the sensor. Okay, the optical encoder. And just for comparison, we also measure the vibration using an accelerometer, and this is the data acquisition front end. This is just a view of the gearbox, where we could see faults in the lay shaft of the gearbox. And this is the input shaft at a certain frequency and the output shaft. Output shaft is connected to the encoder. Okay, we could run the gearboxes at different gear machine frequencies. And these are the gear machine frequencies. These are the different input shaft speeds. We tried 3 different shaft speeds. I had a healthy gear and a faulty gear. We could remove one tooth from the gear. Now, look at the vibration spectrum. Frequency, this is as expected. I can see all the frequencies, F1, F2, F3, and twice of that. This is expected from any standard vibration measurement. But look at this. The instantaneous angular speed amplitude, it can detect the variations of the frequencies of the order of these values, even at the rotational frequencies. So this is the power of using an optical encoder for measuring torsional vibration. Now again, just to give you a cost comparison, I mentioned rotational laser vibrometer cost about 30 lakhs, but this system, instantaneous angular speed, an encoder costs us only about 10,000 rupees. Of course, data acquisition unit another couple of lakhs, and then you can measure the torsional vibration using a very cheap optical encoder. And a lot of PhD students, master students are using it. So people today are looking for alternates to measure torsional vibration, avoiding the costly rotational laser vibrometer. So your optical encoder is a good choice. And you could see for different loads, average RMS, there is a change in the healthy and the faulty gear. So a lot of algorithms can be developed to find out faults in the gear just by measuring the instantaneous angular speed. And today, lathe machines, CNC machines have optical encoders for positioning, and the output from those encoders can be used to find out fault in those lathe machines. You can retrofit a lathe machine, a CNC machine, and to find out faults in that machine. Now, I will switch gears here, again to give you a background as to, we just talked about this transducers from vibration monitoring for finding out the fault in the gearboxes, and be it orbit, acceleration, torsional vibration. But sometimes it happens that many of these measurements will not be done in situ in the field. So again, in the early 60s, people had tape recorders, the same tape recorders which we used earlier. I don't know if you have seen the magnetic tape recorders or the cassette tape recorders. Or today, of course, the young guys and millennium kids may have only be born with CDs and DVDs and Blu-rays, and of course now again flash drives, no drives, just a solid state memory device. Okay, but the technology was such that there used to be a large school. Even today, if you go to the Akashvani Kendras, they have a lot of school recordings of the past years. Okay. And this magnetic tape recording gave way to frequency modulation recording. These were all analog. And then, of course, came the pulse code modulation recording and the digital audio tapes. Because these are the analog recordings. And I remember as a student, we used to carry big tape recorders in suitcases, going to steel plants, putting in accelerometers, measuring the vibration, recording it in a tape recorder, bringing it back to our laboratory to do rudimentary analysis. And of course, those days, even data acquisition was not very, the computer-aided analog to digital converters were also not very common. You know, sometimes in our country, in the early 80s, these data acquisition cards came about. Okay, and I'll come to this analog to digital conversion, because see, there are limits of analog devices. Okay, but as you all know, if any analog recording coming out of a transducer, if I can see it in an oscilloscope, well and good. But if I need to analyze the data, I need to do some sort of a processing of that data. I need that data in an maybe as an Excel sheet column or a MATLAB file. So this brings about what we need to know is analog to digital conversion. So this A to D converters were available, but not commercially popular as in the mid 80s. Okay, so a company in USA, National Instruments, who are very world famous now, they came up with a software called Lab Windows. Okay, somewhere around 1985, 86, they came about the software Lab Windows. Of course, you know, they were on the disk operating system of the PCs, and you have to plug in the card, the analog device card, to the motherboard of the PCs. There used to be ISA bus, okay, or the PCMCIA bus in those days. And that is one recording which needed to be done. Now, having said about recording, let me switch gear a little bit and come back to a little bit on the analysis. Okay, I'll just stop here only. See, it is very important in condition monitoring that I find out the spectrum from the measured vibration. Okay. So what happens in the spectrum if I have certain P? So what is the spectrum? The vibration signal in the time domain converted to the frequency domain. I'll come to the story of conversion to the frequency domain a little later, but it is important in condition monitoring that this spectrum, if there are peaks at frequencies A, B, C, each of these frequencies A, B, C relates to a physical parameter in that machine. So if a physical parameter A has gone wrong, the amplitude at frequency A is going to increase. So that is the power of vibration spectrum analysis. But again, I must tell you, so this spectrum analysis is done by an hardware, or if I have the data, there are certain the Fourier transform of that has to be done. Now, Fourier transform can be done by hand or by a computer. So in the 1950s, when the 54 actually, when the first digital computer came about, people started to use digital computer to do Fourier transform. 1954. And those days, those computations, if I had n data points, they required n square amount of computations. But this was very, very costly in those days because computing power was very, very scarce. So in 1964, two gentlemen, Pule and Take, they were working at the IBM Research Center, Watson Research Center in New Jersey. They came up with an algorithm which required not n square complex operations, but n log to the base 2 n operations. That means n has to be a radix of 2. So n has to be 512, 1024, 2048, etc., etc. And the computation requirement was very, very less compared to the previous digital Fourier transform or discrete Fourier transform, which require n square operations. So what happened? These two gentlemen found out this algorithm, and I think they were being employed by Westinghouse. And then the company Hewlett and Packard, HP, which we know today, immediately hired them. Okay, this gentleman, Hewlett and Packard, and they commercially started to make what is known as spectrum analyzers. They called them as fast Fourier transform analyzers, FFT analyzers, a big hardware. I mean, today we have a two-channel FFT analyzer in our lab from those years. Of course, we bought it in the somewhere in the early 80s in IIT Kharagpur, but the HP analyzers came out to the market in 1969, HP FFT analyzers. Okay, and they were the size of a desktop. Maybe I'll show you a figure. Yeah, this is one HP analyzer. This is when I was a student in US. Okay, I'll just give an example. We are doing this measurement of a John Deere backhoe loader in their Dubuque plant in Iowa, okay, in USA. And this is in their plant. And you won't believe it, we had to carry all this equipment from our lab in Lexington, Kentucky to where I was doing my PhD to this place. We had to go in a minivan. So this is the two-channel HP analyzer. And in those days, we had this DAT tape recorder of TAC. Okay, so what we did is we recorded them, okay, on the different channels. The accelerometers are put, and then we did the analysis. And today, let me tell you, these are all possible with a small laptop and an USB device. Okay, so that technology, and this is sometimes in 1990s, 89. But in 1969, HP started to commercially flood the market with HP analyzers. At the same time, in Japan, Onosoki company came up with this FFT analyzers and commercially they flooded it. But they were bulky. I mean, look at it. They were bulky, 2-channel, at most 4-channel. But again, parallelly, what I rightly told in the beginning, the miniaturization of electronics has made our life as machinery condition watering very, very, I would say, easy. And then this analysis today, you can do more analysis in your laptop, in your iPhone, compared to the those days analyzers, because of the availability of fast processing chips, FPGAs, where you can do your own programming, etc. Now, coming back to my story of recording, so today it is all digital, and then another thing is this: how do you go from analog to digital? So we are talking about the data acquisition systems, cards, lab views, lab windows gave rise to lab views, and today we have very, very USB-based plug-and-play data acquisition units, very, very high sampling frequencies. I'll show you an example again. Okay, so coming back to the data recording, today we can measure digital, It's not only 20 kilohertz, you can go beyond that in my laboratory. I will show you, or there's a picture. We can record 12 channels each at 1 megahertz. Okay. Very, very fast sampling, very fast, and 12 megahertz. Okay. But question is, once it is digital, this data has to be stored. Okay. I must tell you, this is a Sony DAT recorder. This is one of the very first purchases in my lab somewhere in 1998. This is the DAT recorder which can record 8 channels till 10 kilohertz or 4 channels till 20 kilohertz. You can record it in DAT tapes. Sony has stopped manufacturing them, and today, if this is still working today, if I play recordings, say 20 years back, and if I play them back, it will look to you as if you are sitting next to the machine. Okay, this, of course, we have to keep those tapes in a nice air-conditioned environment. But today, these are all gone. We are all doing digital recording, and today, this is a digital recorder wherein I can have voltage inputs, strain gauge inputs, accelerometer inputs. Okay. Similarly, this is the latest one which I was talking about. This has 12 channels. Each can be sampled. Now, I'm not going to talk about the sampling frequency on data acquisition, but the digital, because today everything is to be converted from analog to digital. I can put them in digits, and then I can do the analysis in digits. So this is possible through this kind of data recorders, depending on the memory. If this has 2 gigabyte of memory, with one channel at 100 sampling mega samples per second, I can record for 20 seconds. If I reduce the sampling rate, I can record for 30 days, and so on and so forth. So this brings to a very, very important slide, that the data rate which is transmitted depends on the number of channels of data I'm taking, acquisition rate, and then resolution. How many bits per sample? If each sample requires 24 bit, that means 24 bit means how much? 3 bytes, and then acquisition rate is, so each sample is taking 3 bytes. If I'm taking, say, 1,000 samples per second, 1,000 samples is a very, very low sample. Suppose I'm taking 1 megahertz, so 3 mega samples per second. So this is what is the data rate. So if I want to transmit high frequency data, multiple channel vibrations, the present day capability of data transmission of 100 Mbps or 200 Mbps or 1 gigabytes per second, etc., or gigabits per second. These are the restrictions, and that is why today, when we are transmitting digital videos or audios, a lot of data compression algorithms have come up, okay, where they will compress the data for transmission, and at the other end, we can decompress them and look at the original signal. And the same technique can also be used. And of course, you would have always noticed that even your video streaming, when you are doing, they do some sort of a buffering. This is because of this data rate. So it is put in a temporary memory, and then it is decompressed to make the original image. So, but we are going to live with this, and this is the future. The data acquisition rates has to be very, very high, and then we have to sample signals at very, very fast rates. You have to capture phenomena. Coming back to machinery condition monitoring, as you know, if we talk about audio, we are happy at 20 kilohertz. If you are talking about ultrasonics, the phenomena occurs at about 2 to 3 megahertz. And if you are talking about earthquake vibrations, very, very low frequencies, less than 1 hertz. Okay. So depending on your interest, you have to decide on the sampling rate, otherwise signal aliasing can occur. Good. By the way, just to tell you, we have, if I go to my website, there are about 40 video lectures on this machinery condition monitoring, which was from an NPT, which is my NPTEL program. You are free to go through them also. You go into the details of these. So this brings us to the latest technique of wireless data aggregation. Okay. Because as I was telling you right in the beginning, today we are talking about wireless data aggregation. So we need to capture data because I do not want to lose the phenomenon which is occurring in my machine. So wireless data aggregation can be used everywhere. Remote monitoring of wind turbines, hazardous places like nuclear reactors, inaccessible far off places, okay, large power plants. We cannot be having cables drawn from everywhere. So we cannot. And today there are transducers with wireless transmitters, just sitting on the bearing of a motor or a pump and transmitting to the cloud. We can capture them, and then cloud computing is being done, and you can be downloading it at anywhere and know the condition of the machine. And this is what is the future. I mean, it is coming up. The only bottleneck is the speed at which we can transfer data. And with algorithms coming up, and of course, I'm not going to tell you about what kind of data analysis is being done. I will come to that later on. Physics-based, model-based, and of course the machine learning-based or the soft computing-based. So this is very, very important. Okay. I mean, certain terms people use in Wi-Fi, the frequency band, data rate. Data rate is very, very important. Sometimes it is just not only one accelerometer, but it could be many accelerometers. And then this has to be captured and sent. Just to give you an idea how this is done. This is a three-phase induction motor. I have put an accelerometer. I have put an Wi-Fi device. It will transfer the analog signal, convert it into digital, transmit the digital values over the Wi-Fi. I can have wireless LAN or Ethernet and receive it. So once it goes to Wi-Fi, it goes to some cloud server, and I can receive it. And they could be over wireless LAN. They could be, this is in Alaska. This is, I'm sitting in Kharagpur. Okay, and to tell you, this is what we are doing right now. I am a consultant to many industries in India and in US, where our algorithms are being used for motor current signature analysis to find out faults in motors and mechanical units being driven by motors. And we have a server here. We tell them this is the problem with your pump at such and such location or the motor at such and such location. And that is what is the technology. And this is just a National Instrument device where this is an accelerometer. This is the module which goes into this chassis, which will transmit over the Wi-Fi. So in the laboratory, just to demonstrate, now we had a blower. You can see the accelerometer here. I have this Wi-Fi device, no cables, and you can see the signal being captured over the Wi-Fi. And this we did about 15 years back. Okay, this kind of experiment. But today it is off the shelf. You go to any market, you buy accelerometers with an add-on Wi-Fi transmitter, or Hall effect sensors with Wi-Fi transmitter, current transformers with Wi-Fi transmitters, flow measuring devices with Wi-Fi transmitters, temperature measuring devices with Wi-Fi transmitters. This is very, very standard nowadays. All we have to understand is the right software protocol and database management to keep the data in the appropriate locations. And because, as I was telling you, in condition monitoring, database management is very, very important. Okay. Nowadays, of course, if a lot of data is coming up from a fleet owner, for example, I'll just give you an example. Indian Railways. See, if every locomotive today has an onboard diagnostic module. Okay, they come to the station, they will plug the data logger and download all the history. It's like a black box of a locomotive. I mean, why even locomotive? Even your car nowadays, if you go to the service station, they will bring in a data logger and download all the events which has occurred in your engine. Certain cylinder is misfiring, certain clogged flow valve, etc. Fuel pump not delivering correctly. So these all informations are already stored in an event-based system. When the service technician will plug that data logger and get the information, and the service manager will come to you, sir, your cylinder engine cylinder number 3, the spark plug needs to be changed. He tells with certainty without even driving the vehicle. You will know because they are all being logged, and that is what is the future of database management. So there is an ISO standard 13374 which has come up. So database management of condition monitoring as a system, as an ERP system. For large plants, this is happening. This is going back to the example of accelerometers, the Wi-Fi acceleration which I measured. Okay, is it the acceleration? Okay, and this is the vibration spectrum of the blower. Okay, wire capture spectrum. And the supply frequency of 48.36 Hz. Okay, I will come to this motor current signature analysis and the future. In the afternoon, we are talking about the advances in the motor current signature analysis. So at this point, there are some questions. So let me see if I can access the chat window. I will try to answer the questions. Okay. Well, is this the first question? Okay, good morning, everybody. Now, the question is how to identify RUL for bearings and gears. Is this possible to exactly how much life is left? Can AI ML clearly predict this? Okay. Now, how to identify RUL for bearings and gears? First of all is we must have past data, because nothing is possible without data. So once we have data, and from model-based techniques, I can know that I have to define what do you mean by the possible failure of a bearing. Has the clearance increased or has the vibration level gone to a certain level? So once I define that, I can say that a simple extrapolation of the parameter, measured parameter, by a linear regression will give me an idea of to RUL of bearings and gears, then will apply for gears. But can AI ML clearly predict this? Yes, AI ML can clearly predict this, but then we require a lot of data to find out trends. And today, there are a lot of algorithms. I've seen people take a bearing. In bearing, there is an inner race, outer race, cage. Okay. And then the rolling elements. They try to identify faults, whether there is an inner race and outer race. It has no meaning to us. If bearing is faulty means a manufacturer will not replace an inner race or an outer race. Manufacturer or the user will replace the bearing. So AI ML can be used, and there are a lot of literature in this area. Our next question is, are RLVs specifically used to measure torsional vibrations, or can be used for lateral vibrations also? Well, the first question is correct. Yes, RLV specifically used to measure torsional vibration, that is right. But some of the RLBs have an option wherein I can close one laser beam. So out of the two laser beams, only one laser beam comes out, and then I can measure the lateral vibration also. This is a sales gimmick of the manufacturer. How can you select the transducer for required data? If I understand your question correctly, how can you select the transducer for required data? See, selection, for example, let us specifically talk about vibration transducer, for example, accelerometer. Now, how can you select? So what is there in selecting an accelerometer? It is its sensitivity and it is its frequency range, right? So if I am talking about vibration of an IC engine, see, IC engines operate maximum up to, even at high speeds, unless it's a sports car. Sports car operate about 12,000, 13,000 RPM, but normal IC engines, 5,000, 6,000 RPM, which you use in your car. So 5,000, 6,000 RPM, 6,000 RPM means about 6,000 by 60, about 1,000 hertz. So you see, for data collection from IC engine, a vibration accelerometer, if it has a frequency range of 5,000 hertz, it is good enough. And if you are talking about a gas turbine engine, then we can talk about very, very high frequencies, maybe 10,000 hertz, 20,000 hertz. So it depends. And sensitivity. Sensitivity is also, if you have to have high signal to noise ratios, I put more sensitive accelerometer. But the problem with sensitive accelerometers is because the piezoelectric material is more, the mass increases. So one has to do a trade-off between the mass of the accelerometer and the sensitivity. Right? The question is, how to find out the relation? The next question is, how to find out the relationship between torsional and lateral parameters for gear pair vibration based model. Okay, it is from the geometry, and there are many papers in this area. Even my papers are there. Okay, it is from the geometry. Just to suffice right now, looking at the parameters, you can look at the mathematical equations and you will find it. And there are a lot of papers. You can again refer to the notes where I have referred to one hour paper on gear pair vibration based model. There are no more questions. Is Dr. Sidra there? Or anybody else wants to ask any questions? You can write.
Okay. Participants are encouraged to please participate in the discussion. They can raise your queries. They can write their questions in the chat box right now.
Yeah. Yeah, we have about 10 more minutes. So if anybody is interested. Yeah, let me see. MEMS sensitivity versus piezo sensitivity, can we get same accuracy by using MEMS in the same frequency range? Yes. Okay, but let me tell you, this MEMS based accelerometer are for very, very low frequency, less than 3,000. I mean, for practical purposes, it is less than 1,000 hertz. Okay. Piezoelectric accelerometers, they will work for 20,000, 30,000 hertz. So in that way. Okay. So MEMS are used for, again, temperature is also an issue. For normal room temperature applications, we can use MEMS based accelerometers. And they are very cheap. And people are using MEMS based accelerometers for a detection, event detection, like airbag deployment sensor. Okay.
Any other question from the participants?
Okay, in that event, I will stop here and we will continue our discussion in the second half from this, right? And if there are any questions, you can ask me in the second half at 2 o'clock.
Excuse me, sir. There is one more question right now from
Okay.
Prasad Shinde. That what is the importance of dimensional analysis in fault diagnosis of bearing?
Could you please repeat the question?
It is written in the chart box that what is the importance of dimensional analysis in fault diagnosis of bearing?
Could he be specific? Dimensional analysis has many connotations. What exactly he means by dimensional analysis? Dimension, you mean the dimension of the bearing? I mean, or is that, would you be very specific? Because see, if the bearing, there is a fault, it is at the characteristic frequencies, which depend on the dimensions of the bearing, if you meant that. Okay. So if the ball diameter, the inner race diameter, the outer race diameter are known, these are related to the fault frequencies. Okay. So the fault frequencies and bearings will be identified by the dimension of the bearing. It is not dimensional analysis, but it will be measured or evaluated by the dimension of the bearing.
Thank you, sir. Sir, there are a few more questions.
Yeah, please. Yeah. I mean, can we use AI in CBM? Oh, yes. See, artificial intelligence is a very, very broad topic. Okay, even if you draw a straight line y is equal to mx plus c and extrapolate it, it is also artificial intelligence in a single dimension. So once the dimensions and parameters become large, it becomes humanly impossible to monitor all parameters. And that is why with large data, we use machine learning. Yes, people are using. And today, softwares are there which will treat and then. Yeah, can thermography imaging be replaced by acoustic imaging for electrical discharge? Let me try to understand this. So if there is an electrical discharge, there will be noise. Okay. So acoustical imaging will capture that. Correct. I agree with you. Can thermal imaging, see, thermal imaging is measuring only the temperature. Acoustical imaging is only measuring the noise. Okay. So both will complement each other. It cannot be replaced because the physical parameters are different. Thermography is for temperature, acoustical imaging is for the noise. So you can try it out and they will complement each other. Suppose something you are missing in acoustical imaging, particularly because of the background noise or particularly because of the very high frequency of the electrical discharge, you can supplement or complement it by thermal imaging.
Thank you, sir. You can see one more question in the chat box.
There's a question. So the lamps, let me go back. Participants, auto identifier. $10.52. Can we use AI in CVM? Oh, yes, you can. Then this I have answered. What is the importance of dimensional analysis? This I have answered. Thermography. 1053. 1054. Yeah, I think I've answered all the questions.
Thank you, sir.
Hello,
now, thank you.
good morning. Ronnie, why classes are over? Still you are in there? Hello, classes over. I left a long back. Please, I'm waiting for some other second year. Okay. Ronnie, please leave the class. Go for the next class.
The organizers, please see, there is some now noise. Okay, so thank you very much, Professor Mohanty sir, for your very informative and interesting lecture. Now I am pleased to extend the vote of thanks on this memorable session. First of all, I would like to thank our guest and resource person, Professor A.R. Mohanty sir, who, despite of his busy schedule, has found time to grace this occasion. Professor Mohanty sir has chosen a very important and catchy topic for researchers and academicians who are involved in the area of machinery condition monitoring. I'm sure that all participants must have enjoyed and got benefited from this informative talk. My heartfelt thanks also go to all dignitaries, organizers, and participants. Last but not the least, I once again thank you all for showing patience in listening to the talk and making this event a success. Thank you very much. Now there will be a break up to 11:15 a.m. and after that, next session will start at 11:15 a.m. That will be based on how to choose sensors for condition and monitoring. So all are again I thank you all very much. Thank you.